Okay, let's suppose, hypothetically, for the sake of an example, that there's a pandemic going on. And let's say X is going to be the number of infected people in the US. So here, the number of infected people, this is a system where the state is represented by just one number, the number of infected people. And I want to model how this changes in time so that I can make some predictions. Now, what should x prime of t, the time derivative of x, what would that represent? If t is time, say, in days, then this would be the infection rate in days, how many new people are getting infected per day. So this is the rate of new infections. And this doesn't strictly make sense since the number of infected people in the US is an integer. So this is really an integer valued function. But for the sake of the model, let's just pretend that it's not an integer. So our model may produce non-integer numbers of infected people, and then we must round what the model produces to the nearest integer to get the model's prediction. So that way, there's nothing wrong with taking derivatives like this. Okay, so I'd like to write down a model, a differential equation. If I could just predict what is x of t right away, then I would write down that prediction. But instead, what is more readily available is a way of describing a relationship between x and x prime. So it will be a law that governs how x changes in time. It's so okay, what should the rate of infection be? Or how will it be determined? New infections are caused by existing infections. It's reasonable to think that if you double the number of existing infections, then you double the rate at which new infections are created. If you halve the number of existing infections, then you halve the rate at which new infections are created. It's a simplified model, if that's not strictly correct, but let's just go with it. So what I'm suggesting is x prime is proportional to x. So x prime is something times x, and there's some proportionality constant. I don't know what it is, but let's just pretend it's 3 so that we have some number. So I'm not sure about this 3, but we'll just put something there for now. Okay, so let's suppose x prime is 3 times x. It does matter that this number is positive, because that's telling you that the rate of new infections is positive, so you are getting more infections over time. And how many more per day is proportional to how many there are at any given time. Now remember, this way of writing a differential equation is a lazy shorthand for this. So here it looks like there's no time because you don't explicitly see t's showing up, but the time is implicitly there. All right, so if we can solve this differential equation, if we can find x that makes it true, then we will have some predictions from this model as to how the number of infections changes in time. Okay, so the first thing I'll do is divide both sides by x. And as soon as I do that, I'm assuming x is not 0. So let's assume we only care about situations where there are infections. So then I've got this. And now I'm going to do something that looks like it's coming out of nowhere. But it's okay, just let it go. We'll eventually develop some techniques that allow you to deal with this and other situations in general. So here's my step that looks like it's coming out of nowhere. the left-hand side here is the log of x, the derivative of the log of x. If you just use the chain rule and take the derivative of log x of t, then you should get x prime over x. Okay, so that you should, if you need to review, how to take derivative of log or how the chain rule works, you should verify that this evaluates to this. Okay, how does that help? Well, now this is a much easier kind of question to address. Now the question is, what kinds of things have as their derivative 3? So here's one example of something that has as the derivative 3. It could be that log xt was 3t. 3t has its derivative being 3. But that's not the only example. It could also be that log xt is 3t plus 1, or maybe 3t plus pi, or 3t minus 100. So there are actually many possibilities as to what log xt could be in order to make its derivative be 3. Let me actually keep that stuff up. So from here, to write down the most general possible thing that could happen, log of x of t is 3t plus some constant. That's what we can conclude from here. So if x is a function that's known to satisfy this, then we know that this is true for some number c. Now, our goal was to get x of t, so let's exponentiate both sides. By the way, whenever I write log like this, that's the same as ln. It's the natural logarithm. So log is not like the log on your calculator, which sometimes refers to log base 10. This is log base e. I'm just used to writing log. I also don't like ln because, well, I have no good reason not to like ln. Okay, so x of t would be e to the 3t plus c for some constant c. There's actually a nicer way to write this. X of t is e to the c, e to the 3t, for some constant c. And if c is just some constant, then so is e to the c, right? E to the c is some positive constant. So we could say x of t is this for some positive constant a. And here's our exponential growth model. The number of infected people grows exponentially. And of course, that's not what really happens in real life. It's a simplified model, but it sort of sometimes happens when all the assumptions that the model requires are not violated too much. So we started with a differential equation here, and after some work, which is represented by this wiggly arrow, we reached a solution. And I'll admit that one step was a little bit mysterious from here to there. It may have been tricky to realize that the left-hand side here is the derivative of something. But just letting that slide, hopefully that was okay, going from the differential equation to the solution. Now, is it fair to say it's the solution? It's not really one function. It seems to have this free parameter a. When I do this, when I write down all the possible solutions like this is called the general solution. So what I have found is that there's more than one solution to the original differential equation. x equals 5e to the 3t is a solution, and so is x equals 7e to the 3t. They're both solutions. So is x equals e to the 3t. If you want to check, just substitute them into the differential equation. So for example, 5e to the 3t. If x is 5e to the 3t, then x prime would be 5 times 3 times e to the 3t. And if you substitute this into here and this into here, you should get a true equation here. And hopefully you can see that it doesn't matter whether what's in front here is a 5 or a 7, it'll work no matter what. So what we have here is the general solution, which means a solution with free parameters in it. Such that, so here I'm referring to the a as a free parameter. Such that all solutions are described. It's a bit of weird terminology. I actually really don't like the terminology general solution, because it makes it sound like it's one solution. It's really a family of solutions. So it's a little bit weird to say a solution. It's a family of solutions parameterized by some parameters. And it's weirdly called the general solution if all solutions are being described. So this is as opposed to a specific or a particular solution. Like 3e to the 3t would be a particular solution. ae to the 3t would be the general solution. 5e to the 3t, 7e to the 3t, those are particular solutions. Okay, well, the point was to make a prediction, right? So can we do that here? Can we predict how many infected people there are at time t equals 100? What that means, I guess, depends on the units of t. Maybe it's days, 100 days. Can I just plug in 100? X of 100 equals ae to the 300. Well, I don't know what that is unless I know what a is. So I cannot make predictions unless I have a particular solution in hand. So what's missing is initial conditions. So in addition to the original differential equation that was part of my model, I need to put in an initial condition, which means a specification of the state of the system at a particular time. It doesn't have to be time 0, but usually we set up our time axis so that it's conveniently time 0. Here's an example of an initial condition. X of 0 equals, so let's say at time t equals 0, we have 30, let's say 40 people infected. So that's an initial condition, a specification of the state at least one time. If I know that x of t satisfies the differential equation here, if I know x of t satisfies the differential equation here, and I know it satisfies the initial condition, then I can start making predictions. Because the initial condition allows me to solve for the free parameter here in the general solution to get a specific solution. So the differential equation gave me the general solution. If I now impose the initial condition, so I'll demand that the initial condition hold, that it works, then what do I get? So the left-hand side is x of 0. That's ae to the 3 times 0, which is a. And the right-hand side is 40. So it looks like the initial condition requires that a be 40. So that tells me that x of t equals 40 e to the 3t is the only function that satisfies both the differential equation and the initial condition. This is something I can make predictions with, plug in different times and figure out how many people are infected at different times. So in this situation where you have a differential equation like x prime equals 3x and an initial condition like the value of x at a particular time, maybe 0, the whole setup is referred to as an initial value problem. And to summarize what I was saying earlier, given an initial value problem, that you can get a particular solution. So given only the differential equation, we got a general solution where it's a whole family of solutions. Then given the full initial value problem, there was a particular solution that we could use to make predictions. So hopefully that makes some intuitive sense. In order to predict the state of a system, if what you know is how the system changes, you need to also know how the system started out, right? Okay, and I also just wanted to show you a plot of the solution we came up with. So it was 40e to the 3t. That was a solution to the initial value problem up here. And you can see is this exponential growth starts at 40, so the initial condition sort of pinned down our solution curve here. And what you're seeing is time on the horizontal axis and x, the number of infections, on the vertical axis. And the curve represents the number of infections evolving in time according to the differential equation, x prime equals 3x. And another fun thing to look at is what happens if you change the initial condition. So if the initial condition, instead of being 40, is a, where a is a possibly different number, what do you get? So we can create a little bar that we can manipulate for a. Let's say I'll look at the different a's in the range 30 to 50. You can see it changes the curve, the shape of the curve, but the general appearance is the same. Well, yeah, so to be clear, what we're changing here is since plugging in t equals 0 into this expression gives you a, what we're changing when we change a is the initial value of x. So we're changing the initial number of infected people. So as I drag this bar left and right, you see the initial number of infections moving slightly up and down here between 30 and 50. Let's allow it to go from 30 to how about up to here, up to 600. So you can see the initial. This is what I'm basically manipulating, where the curve is pinned down on the y-axis, or I guess on the x-axis, since the vertical axis is the x-axis. Yeah, so if you want to visualize the general solution to a differential equation, then it's not just one graph, it's an infinite family of graphs, and you have to think about all of them. And next we'll see some, or pretty soon we'll see some way of visualizing, trying to visualize all of them at once.